General of UNESCO that the ocean is a new frontier, and that this is a decade will provide the framework for international coordination and partnership to reinforce research capabilities in marine science and transfer technology. Among these challenges, coastal inundation and erosion is one of the most urgent. The densely populated coast of East Asia and the Pacific Island are especially vulnerable to inundation and erosion related hazard. Accurate prediction of this hazard hold the key to success of our engineering countermeasures. During the past decades, we have made remarkable progress in observation technology and prediction models and big data. In the coming decade, we need to find the innovative solutions to better predict and monitor the hazards. This will be done through the international research cooperation on the UN Ocean Decade Program. Today, we are here to identify the problems in our current practice and discuss solutions through the international cooperation. We will explore the possibility of devising an action program for the UN Ocean Decade that specifically targets the region's coastal inundation and erosion. As the Vice President of Ocean University of China, a top university in ocean, a top research university in ocean science and technology, and as standing member of the Fourth Council of the Chinese Ocean Engineering Society, and the chairman of the steering committee for higher learning program of ocean engineering of the Chinese Ministry of Education. I will fully support the implementation of the program. Let's join hands to effectively address the coastal hazard and other ocean challenges. Together, we shall contribute to the well-being of humanity and the better future for our plans. Thank you for your attention. Okay.
Thank you very much, Professor Lee. And thank you again for your strong support to this program. It will be very helpful. And we'll go to the next the presentation sessions. First speaker is Dr. Yan Kun from Deltares. Deltares is a former Delft. They involves lots of activity, developing software and also many international corporations. Dr. Yan, please. Dr. Yan, are you here?
Hi, Mr. Lee. Good afternoon. Sorry for interrupting, but we would like to make a group photo before the continue the session if it's possible.
So how can you do that?
And everybody, please turn on your camera if you have one.
So everybody turn on the video. Is it right?
Yes.
And I'm curious, Dr. Yan, are you here? Are you still sleeping? There's a big time lag here in the Netherlands, so if you are here, please join Dr. Yan. Can you take a picture? Oh.
I haven't seen your first speaker in this room yet. Let me go and check my colleague quickly if he's at the plenary room.
I think it's early in the morning, maybe 5, 6 o'clock in the morning in Netherlands. So I'm sure he's in here, but did you find Dr.
I
Yan is here?
can't find Dr. Yan's name in the list, in the name list. I can't find Dr. Yan's name in the here. Maybe later we change the second speaker.
Okay, is it okay? We move to second speaker, and if Dr. Yan is coming, probably he will talk. How about the second speaker? Dr. Yu from Kiosk.
Yes.
He is an expert in the video and radar observations. He studied at the University of Georgia Tech, isn't it? And he's working at Kiosk. Dr. Yu, please.
Yes. Okay, just a moment.
So I need to turn off.
Hi, everyone. I am Jason Yu, working at Korea Institute of Ocean Science and Technology. Today, the topic I would like to talk about is nearshore bathymetric monitoring using ground video and expanded radar for operational coastal inundation and erosion hazard prediction. In my presentation, I will introduce backgrounds about the use of remote sensing for coastal observation and briefly explain the concept of ground remote sensing based wave measurement and lastly, depth inversion and monitoring. Conventionally, in situ sensors have been used for coastal ocean observation and surveys. However, this approach is slow, labor intensive, and expensive. In the meantime, remote sensing based ocean observation provide continuous monitoring with high temporal and spatial resolutions, covering wide coastal areas. For example, in order to measure wave characteristics, several remote sensing platforms have been developed, such as satellite, airborne, and ground, coastal radar, and videos. A remote sensing approach to directly measure water depths has been also developed, but this is limited for muddy waters, in which light cannot penetrate to the seafloor. In contrast, if we can collect ocean surface images, we can estimate water depths from imagery based on linear wave theory, which relate wave properties and to the water depths. Radar is one of remote sensing tools to observe ocean surfaces. When it is installed on the ground above the shoreline, its coverage is from the shoreline to optimally 2 kilometers. These are examples of expanded radar images collected around Korea, showing wavy sea surfaces on the left and calm sea surfaces on the right. Optical imagery, including video, can be also a remote sensing tool to observe coastal seas. Generally, optical imagery has less coverages, but higher resolution than radar images. So it is much useful to monitor detailed beach processes such as wave dissipation, wave runoff, coastal inundation, and changes of coastal line and depth mastery. Even though it is limited for storm weathers and black night conditions. How to quantify properties of ocean surface waves from remote sense images is based on the concept that image intensity signals have high coherence with actual wave signals. So using information of wave paces seen on the left image, we can estimate wavelengths, wave period, etc. According to the ocean wave mechanics, wave properties in the coastal area experience wave transformation, such as wave diffraction, reflection, dissipation, shoaling, breaking, as shown in these figures. Waves are dispersive and transformed during the propagation with a certain relation among the wave period, wavelengths, water depths, and currents. This relation is called dispersion relation. This is a synthetic example of dispersion relation in 3D expressed in the wavelength axis in X, Y directions and wave frequency axis in Z direction. So the 3D dispersion relation results are computed from the 3D image data and can be visualized in this example shade. This is an actual image of dispersion relation computed from radar image burst. We define the area of scale for wave property analysis, collect 3D data cube from the area, and apply 3D FTFT, 3D fast Fourier transform to compute this dispersion relation. This shows the detailed procedure how to estimate peak wave period, wavelength, wave direction, and even wave height from the 3D FFT result. This shows an example of wave height measured using an expanded radar system called WAMOS in the North Sea in the Northern Europe. This time series trend shows a good match with in situ measurement. In this slide, the wave measurements of wave period and wave direction using the expanded radar system were compared with in situ measurement. Both of trend also show good matches with the V measurement. Surface current also measured by the radar system and compared to the numerical model result is also showing a good match between them. Basically, depth imaging method using coastal imagery and wave dispersion relation can be categorized into two groups. The first one is the 3D fast Fourier transform result-based method, and second one is wave phase information-based method. As I explained just ago, this slide shows that water depths can be estimated from the 3D FTFT result by finding dispersion relation shell shape from it. This is an example of water depths are retrieved from the 3D FTFT result and dispersion relation. The second method of depth inversion is to use information of wave faces detected from the coastal images. To begin with, this method is to detect difference of wave faces over image domain between these two successive images collected with a certain time interval. Then it computes wave phase speed using the phase difference and the time interval, thereby invert the wave phase speed into water depths using the wave dispersion relation. This is an example for measuring wave celerity and water depths using phase information from radar image data. This is one more example for measurement of water depths using wave information from optical image data. When the barometric results derived from the imagery in the middle or compared to the field survey result on the right, the comparison show quite good match. To summarize, we can continuously monitor coastal ocean using ground remote sensing platforms with inexpensive installation and maintenance. In particular, real-time video can be used to observe the detailed processes with high resolution. In the meantime, radar can be used to measure waves and bathymetry with wide coverage in all weather conditions. Furthermore, the remote sensing-based coastal monitoring can be extended to investigate impacts of climate changes and incorporated with numerical simulations. Thank you.
Thank you, Dr. Yu. We believe that expanded radar has lots of potentials in monitoring directional wave, surface current, bathymetries, and also swash motions. So we expect that lots of applications of radar in monitoring the coastal waters. Thank you. Is there any questions from the audience? Okay, if not, we'll move to next speaker. Next speaker is Professor Platon from Songkya University in Thailand. He will give us a talk on the status of coastal inundation, coastal erosions problem in Thailand, and how to deal with the problem in Thailand. Professor Platon. Oh, yeah.
Sorry, I try to connect to my presentation. Okay, my turn. Thank you very much, Professor Dong Young Lee. I would like to take this opportunity to share some experience about the coastal erosion in Thailand, because many people think about the impact of the climate change and the sea level rise, and people think that the coastal erosion is the primary cause of the coastal erosion is because of the sea level rise. But I would like to share in another experience that the coastal erosion, especially in Thailand, is not the primary causes of the coastal erosion are actually not from the sea level rise, but because of the coastal construction in the coastal area, especially along the shoreline. And we show that the primary cause are one of them are the construction of the jetty. And so, and we have the deposit in one side and the coastal erosion in another side. And then we implement a lot of measures and construction to cope with the coastal erosion. But the method we use to deal with the coastal erosion is cause more impact to the coastal, especially the seawall. And we can say that the seawall is actually not the method to prevent the coastal erosion, but it accelerates the coastal erosion because of the refraction of the wave, and it's called the loss of the sand in front of the seawall. And after construction of the seawall for many years, you can see that the sandy beach disappear from in front of the seawall. And even that we have to construct even the stronger seawall, bigger and bigger, but it still cannot solve the problem of the coastal erosion in Thailand. And especially one important thing is that at the end of every seawall, we call it the end effect of the seawall. When we construct seawall and finish in this area, so it's after the seawall, it has the area of excess erosion in every area. That after we construct the seawall, it increases more coastal erosion in the another area next to the seawall. For example, we call it never-ending story of the coastal erosion management. When there is a coastal erosion in one area after the seawall, then we construct another seawall, and the people complain again that there's a coastal erosion in the village 3, for example. And then if the third village construct the seawall, then it cause more coastal erosion in the next village. And it's never-ending story. So now we have to think about what is the suitable methods to deal with the coastal erosion, whether to construct more seawall or just to stop construct the seawall and set up some setback zone. So we recommend that instead of construct the seawall, never-ending story, but we just stop it and compensate the area that have excessive coastal erosion. So this is some recommendation. There are many cases in Thailand that we have a human development on the shoreline, and it causes a coastal erosion because of the end effect of the coastal erosion. And this is some classic example when we construct the jetty here. The deposit, the land deposit in one side and cause coastal erosion in another side. At that time, we have a full offshore breakwater, and then it's caused a coastal erosion next to the last one. So we construct the new 14 offshore breakwater. But at the end of this offshore breakwater, it has coastal erosion next to the lastest offshore breakwater. Oh, sorry. So we found this construction of the jetty in, let's say, 70 places along the Gulf of Thailand, and it has the land deposit in one side and cause a coastal erosion in another side. And Thailand invests a lot of money for the construction of the offshore breakwater and the seawall, and it's never-ending story. And people always dream something about this. When the government agency told the people, local people, if we construct the seawall, we will have a beautiful beach that we have tourists that can go to the beach easily. But after a year, we can see that the beach disappear. All of the beach disappear from most of the seawall in Thailand. Then we lost the beach. That is benefit for the tourism. So this is some kind of the causes of the coastal erosion. But now we come back to think about the green solution, like the concept of the living shoreline. So we try to go back to understand the nature of the beach, nature of the coastal ecosystem that they prevent the coastal erosion. So think about that. And in Thailand, we have implemented some of the nature-based solution by applying the concept of the beach nourishment, or even the bamboo fence construction to we learn from the mangrove, the roots of the mangrove, that they can prevent the coastal erosion. So we use the bamboo stick, and then we expect the high sedimentation rate after the bamboo line, and we plant the mangrove. We try to reactivate reforestation of the mangrove back to normal, into the normal, like in the past that we have, like in this area, it used to be the mangrove area, but some of them are uses for the coastal aquaculture, and then it causes a coastal erosion in this area. So at first we try to use this concept of the bamboo stick, and then we plant the mangrove after the mangrove, after we have a high sedimentation after behind the shoreline. So we plant the mangrove, we try to plant the mangrove. We don't like the bamboo stick, but what we need is the mangrove forest that we can be prevent the coastal erosion in the future. And now in Thailand, we try to apply the concept of the sand fence, the west sand fence on the sandy beach, and we have some experiment in some beach in that we can see the high sedimentation rate after the bamboo, after the sand fence. So this is the new technique that will be apply in some area after we try some experiment in many places in the Gulf of Thailand and in the Andaman coast of Thailand. So actually it's like the shore, the living shoreline of the forest, the plant community along the shoreline, try to reactivate the sand dune, the sandy beach, and also the coastal forest back to the nature. We call it reactivate the living shoreline. So this is some lesson learned from Thailand. In the past, that we normally use the hard solution to cope with the coastal erosion in Thailand, and it failed, and it increased the erosion intensity in many places, especially in the Gulf of Thailand. But now we try to move it to the green solution, and even we call it the white solution. Green solution means to reactivate the living shoreline, like a beach nourishment, dune nourishment, or even the rehabilitate the mangrove and the coastal forest. And in the future, we try to implement the retreat, the setback zone. Like it should be, because even we have we understand that we are going to have the sea level rise, and the climate change, and the intensity of the wave is higher in the future. So I think the setback zone is better than the hard solution, than to fight with the nature. So in the future, we expect that we will have more knowledge, more the good governance management, and try to control the new coastal construction, or even the remove of some of the seawall, and set up the setback zone for the coastal area. So this is in the future that the Thailand is thinking about that in the future. So this is my last slide. So the lesson that we learned from the coastal erosion in Thailand, they show that we understand that the average sea level rise in the Gulf of Thailand is about 3 millimeters per year, because some of them are also have a problem with how to say, in some areas it's higher than 3 millimeters because of the sinking of the land, I think. Yeah. And because the climate change increase the intensity of storm surge and cold surge in the Southeast Asia, especially in some years in the Gulf of Thailand. we have a problem with the cold surge in some years. Actually, I go to the last slide. Okay, hang on. Okay. Okay, let me go to my recommendation for the last slide. The key issue, like for example, in Thailand, is the coastal erosion is actually the national hazard. Yeah, we accept that, but it induced by the human activity and the coastal construction. And still in Thailand, we still have a misconception of the coastal erosion prevention and mitigation. That in the past, we normally use the seawall and the offshore breakwater to prevent the coastal erosion. But those construction cause more erosion, more coastal erosion into the next beach. So the capacity building that we need for Thailand, and I think we can have this opportunity to share the knowledge between the country in the region. So we need a platform for knowledge sharing between the stakeholder, between many level of stakeholder, even for the policy maker. Let them understand what is the problem with the coastal hard structure, and we need a public awareness program to increase the understanding of the coastal erosion. What is really the causes of the coastal erosion, and we need to strengthen the capacity of the coastal community to adapt to the coastal erosion, not to fight with the nature by implement of the seawall. And we need more research on the living shoreline management, how to restore the shoreline, the living shoreline. For example, the sandy beach, the coastal sand dune, the coral reef, the sea glass, and the mangrove, because this is the shoreline that can prevent the coastal erosion. Thank you very much.
Thank you, Dr. Platon. It's very interesting to see that you are using the coastal habitat, mangrove and coral reef to protect the beach. Is there any question from the audience? If not, how about Dr. Yan? You speak about your activities in Delft, Netherlands.
Sure, Professor Lee, thanks for having me here. I would like to share my screen at this moment so I can present what we did here in the Netherlands in Deltares and what we could contribute to the UN Ocean Decade. I assume you can hear me clearly?
Yes.
Okay. Good afternoon, everyone. Sorry again for the technical issue. My name is Kun Yan. I'm a senior researcher in Deltares. Well, I was invited to speak about several issues that we share globally, like extreme sea level, coastal inundation, coast erosion, and I'm happy to share some of the work that we have done in Deltares. I would like to focus on first from a global perspective, and then zoom in to the local levels and try to seek for collaboration with everyone here, especially in Asia Pacific, and see how we can cooperate with each other and contribute to the UN Ocean Decade. So first, what is the big picture here? So as I said, the sea level is rising, the climate is changing, so we are facing constantly threats from the sea, including extreme sea level, inundation, erosion, etc., which is a subject of this discussion. For accurately simulate the coastal flooding, extreme sea level, we do need tools. That includes accurate models, and forecasting systems that we're looking at, either short-term real-time forecasting or long-term climate change impacts. To build the models and tools, you need softwares. I'll go a little bit into detail that how the Deltares tackle this issue by building softwares and models. And also, of course, the long-term changes like sea level rise needs to be looked at. So for that, you do need a data set, long-term time series, and statistics to understand the long-term increase of coastal flooding and impact. For that, we do need a global data set. Of course, real-time forecasting, early warning is also very effective tool to deal, give you the rooms for evacuation, for disaster risk reduction when extreme event comes. So forecasting systems is also very important. We'll look at the issue from a global scale because there are many places in the world where, which is data scarce areas that requires attention. But also, if we zoom into the local areas, the local details, local data, and also the stakeholder participation is very, very important. Just very briefly for introduction of Deltares. Deltares is a independent private institute. We're working on smart solutions in the field of water and subsurface. And we are a knowledge institute. We are the first knowledge partner of the Dutch government. And we share our knowledge and work. We have experience globally. And we are a strategic partner and trusted advisor internationally as well. So we have around 877 employees. Nearly 80% of them has a university or PhD degree from nearly 40 nationalities around the world. We're stationed in Delft, the Netherlands. However, we do have regional offices in other countries in the world, for example, Abu Dhabi, in Singapore, Indonesia, USA, etc. First topic I would like to touch is global extreme sea level. To understand this, we do need a tool, a model to understand, say, the coastal extreme sea level under interaction of tide and storm surge, and also increasing sea level rise and the changes in the in wind fields and pressure at the mean sea level. For that, we build a global tide and surge model for the entire world. So this is a global 2D barotropical model. There is no boundary conditions for such a model because it is global. So tide force are generated within the model. It utilizes the unstructured grid based on Delft 3D flexible mesh. So there is several advantages of using unstructured grid that I will touch later. The resolution on a global scale is reasonably high. It is in general 2.5 kilometers along the coast in the entire globe. But in Europe, we have even higher resolution of 1.25 kilometers. And some areas even up to 800 meters. For a global model, this is a quite high resolution. So the process we include in such a model are, of course, tidal forcing, the bottom friction are included, but also the self-attraction and loading and internal tides through the friction dissipation are also included, allow us to simulate the global tides accurately. Because using flexible mesh, so the simulation speed, the performance is actually quite good. For a 10-day simulation, it took something like 5 hours on an 8-core machine. Note that this model can be parallelized, can be partitioned in, it basically can be divided into multiple domains and running in parallel on a multi-core CPU. So it will increase the speed. Regarding the accuracy of the model, you can see here in terms of IMS, the model compared to the measurements has pretty decent statistics around the whole globe, and it is improving. So we're using updating the model with the latest bathymetry data, looking at improving tides, etc. Okay, the software that we use to build the global tide and surge model is called Delft 3D flexible mesh. As you can see here, the advantage, the flexible mesh is based on the original Delft 3D software. The advantage of such a model is that the flexible mesh, which is a combination of triangle and different shape of polygons, allows you to construct a flexible model that includes the dynamics of the 1D river, of the 2D estuary, where you require inundation, hydrodynamics, etc., as well as you can go for 3D in the coastal and deep water areas where transport process, salinity temperature become important. Such a model, you can focus on well, detailed areas like harbor and ports with higher resolution, whereas in the deep water, you could use coarse grid to save your computational power. This allows us to simulate the global tides and surge in a reasonably efficient manner. Once we have a model, we want to expand this globally to understand the extreme sea level patterns under especially sea level rise and climate change. For that, we build a global extreme sea level data set based on multi-model ensemble. This multi-model is CMIP6, which is the latest global climate projections, but we use high resolution MIP, which is a high resolution version of CMIP6. We included 5 different model ensembles, run the simulation based from the year of 1950 to 2050, 100 years of period, including the reanalysis period and the future climate projections. This data set, including full time series and advanced extreme value statistics, are made freely available in the Copernicus Climate Data Store by end of this year. Now I'm talking about the simulation, the handcast, the reanalysis, and climate projections. However, early warning and real-time forecasting is also very important. You would like to maximize your lead time before the extreme event hit. So you want to take appropriate actions before that happened. For that, you do need a forecasting platform. Deltares developed Delfuse, which is an open data, open platform for data handling and workflow management tool that allows to construct flood forecasting systems in a flexible way. So here you can see in a nutshell about the modules and functionalities in Delfuse. We can manage large data sets. So nowadays, you know, the numeric weather predictions, the handcast forecasts, or models become more heavy, and the data become unstructured, even 3D data. So it become increasingly complex. And we do have the data management module to manage import, export, store data in the database temporarily, or archive that in the long-term database. Speaking about forecasting system, of course, you need models. You need hydrodynamics. You look at waves. Perhaps you need swan, water quality, even particle tracking, hydrological model, etc. All different kind of, say, models, whether it's commercial or free software, can be fully integrated into their fields, allow certain simulations. And our platform is connected to the mobile internet age, that is fully connected to the web services, allows you to project your data any website. And also it is cloud. We use cloud native solutions. That means our system can be run in the cloud. And it is fully operational. That means it is automatically the system automatically running for 24/7 without human intervening. And yeah, we are also gradually moving from building forecasting system to providing forecasting as a service, which is a new concept at this moment. very quickly on the Deltares architecture. So this is basically what I said. You got weather forecast, satellite images, measurements, field measurements you can import into such a system. All the data process tools are there, allows you to do all kind of interpolation, extrapolation if needed, and then interact with external model. Here could be Delft 3D, could be say Mike or other models. And then your data can be stored in a database, visualized and export into various by various means, internet or archive, etc. For such a system, you could also choose two different flavors, either client server or standalone. Client server, that means you could have multiple clients to or log into the system where database and computing nodes are treated separately, or standalone, that's everything included in one package. For Deltares, we implemented the system and has a partnership all around the world. Right now, like more than 50 countries in the world has used Deltares for their forecasting system for various purposes. Just to bring this into perspective, the global tidal surge model, when it integrated into Deltares, we create global storm surge information systems. This is a operational 24/7 systems that provide global tide and surge forecast for the lead time 7 to 10 days, every 6 hours. It uses Noaa GFS as a native forcing at this moment, and output locations all around the world, and has more than 40,000 output locations on the global coastline. And it is hosted in Deltares, and the data set is also, well, the forecast is also provided freely available via the web viewer called Blue Earth Data, which I will come into, I'll introduce this later. So we're talking about global systems, but we also care about, say, local environment, the local, models, let's say. In collaboration with HAI and Kaset University in Thailand, we built a storm surge and wave forecasting system for Gulf of Thailand based on Delft 3D FM and Deltares. So the model, as you can see the architecture here, that has a swarm model, simulated waves, and deep flow FM model, simulated hydrodynamics. The two models are online or dynamically coupled to allow the interactions between the wave and surge and tides, and also the wave setup and tide and surge calculated to derive the total water level. That will in turn determine the coastal inundation here. Well, the system was put into test basically because of the Pabuk storm that occurred in January 2019. This is a tropical storm, but it did cause a lot of economic damages, and eventually more than 6,000 people needs to be evacuated. It's very nice to see such information coming out from such forecasting system we put into practice and use by the Thai government for disaster risk reduction. The forecasting that coming out of the system were actually prepared and made it available in a web viewer, and the risk area under the storm surge are also presented nicely on web viewer, such that this information can be understood by the public and easy decision making. So because of the forecasting accurate information provided, say Thailand is able to evacuate, as you can see here, people to avoid say further damages for the Pabuk storm. This is an excellent example about how early warning, effective early warning works in a local extreme event. after early warning, I would like to jump into coastal flooding, which is also an important topic. Again, a global data set. We, together with Microsoft, we built a global high resolution, that means 90 meters, flood maps, also looking at the existing conditions, the current conditions, 2018, and also the conditions in the future under sea level rise and climate change. This global data set is made available on the Microsoft Planetary Computer, which is also freely available for the general public. They say because it's a high resolution, 90 meters, we actually produce the flood maps on the cloud based on Microsoft Azure that allows us to quickly produce multiple maps based on different return periods and different global DEMs. That's MERIT DEM, NASA DEM, which is a high resolution based on SLTM, and a LiDAR DEM constructed by Deltares, which focuses on low-lying areas. And these maps are presented based on both present day and on the sea level rise in the year of 2050, such that you could understand the changes of the flood-prone areas due to sea level rise. If we're talking about, say, local floods, at this moment, if we're talking about coastal local floods, so most, at least a big part of the flood damage is caused by so-called tropical cyclones, typhoons, or hurricanes. And those events are highly unpredictable because cyclone tracks has huge uncertainties. And for simulate such an effect, I can imagine you need an ensemble approach. For doing so, you need a fast dynamic approach. We developed Sphinx, the super fast inundation of coast models that allows to simulate the coast inundation process in a rather simplified manner. What is nice about this model is it can include multiple compound processes in the coastal area. That includes pluvial, fluvial flooding, the tide, storm surge, and coastal waves that all combined in the area and simulate the effect. This is an example of the Jacksonville in the USA during the Hurricane Irma in 2017. That this inundation simulated compared to also the measurements and the traditional Delft 3D models. The model itself is super fast, so allows efficient simulation of coastal inundation. Professor Lee, how much time do I still have? I believe I'm a bit over time. Are you on mute, by the way? I cannot hear you. Okay, I'll just continue. I have two small slides. I'll be fast. Speaking about all the data and models, Deltares also created a open website, which is a global open data platform, allows us to share all the data to the general public. So here, this Blue Earth data is basically a web viewer that shares real-time forecasting, the handcast, the reanalysis, the climate projections of all different global data, global systems, global models that we have here in Deltares. So this includes the GLOSSIS, the Global Storm Surge Information System that I just introduced, and GLOFIS, which is a real-time hydrological forecasting system for rivers for the entire globe. The Shoreline Monitor, which is the data set for the shoreline retreat and beach growing for the entire world. And we also include a Meta-Ocean database. And there are more global systems that are coming. All of these data are shared with the Blue Earth data. The Deltares motto is there to share. So that means we would like to make all the data set and tools open and invite for collaboration. And the data is easy access through different APIs, and you can also use third-party data services to get access to data. As I said, this includes time series, 2D maps, etc. And here is a link for the Blue Earth data. If you just simply Google Blue Earth data, you could find out the address for the website. Please go ahead and check and see if there is anything that is interesting. Okay, so this is my last slide. My main takeaway messages is that, well, Deltares is deeply involved in the extreme sea level, coast flooding, and coast inundation work around the world. So we would like to call for a global collaboration or cooperation by using the global data and models. Because of the global data and models, we can provide the local boundary conditions for any local detailed studies. For example, the Thailand storm surge forecasting system. And we're not only focusing on coastal flooding and erosion, but also other applications such as particle tracking, water quality, ecological application as well. So yes, we are open for collaboration and we are there to share. Thank you very much.
Thank you, Dr. Yan. Your detailed introductions of your activities in Deltares. We appreciate Deltares very much because you are sharing the software you developed with engineers, scientists all over the world. It will be really helpful. And you are helping establish the Delta in many places of the world. It may cost you a lot of effort and time of your members. Let me ask the questions. Who is paying your time?
Yeah, well, we're a research institute, we're independent. So that means, yeah, we do need to get projects to finance our own research. But we also get access to fundings, for example, in the European Commission, in the Dutch government, which allows us to do applied research in those areas.
How about the countries participating in the Delta Fuel? What they do? They support finance your time or?
Yeah, Delfuse is a free software. Everyone can use it. But Delfuse is also community-based software. That means we create a global user base or with more than 50 countries. They all use a system, and then say they contribute the development of the system through projects. That the Deltares experts can also join the project team and provide our knowledge, experience, and advice how to build the best local forecasting systems for our clients.
Okay, thank you very much. We'll proceed to the next speaker, Dr. Diana Su from Guangzhou, China. He will talk about, introduce the storm surge inundation forecasting system is established using often COM using the highest, fastest computer in the world in Guangzhou. Dr. Su?
Okay. Excuse me, sorry. Probably the network is not so good. Can you hear me?
Yes.
Hello?
Yes.
Okay, that's good. May I share my slides? Okay, now can you see my screen?
No, not there. Why don't you share it using the button in YouTube?
Okay.
Oh, yes, now.
Okay, that's good. Thank you very much for having me here. Thanks, Dr. Lee, for the invitation and give me this opportunity to share my some of the work. I'm going to continue the previous interesting presentation since I'm also a modeler. My name is Diana Xu. I'm from Southern Marine Science and Engineering Guangdong Laboratory. at Zhuhai. And our project PI is Professor Dong Wenjie and Chen Changshen from Song Yixian University. And these three guys, Yang Jie and Dao Fuhai and Wang Song, are my colleagues. Okay. My topic is about operational forecast of the coastal inundation around the Guangdong, Hong Kong, Macau, Great Bay Area using season model system. Okay, my outline is pretty simple. Okay, first of all, I will review the status and the challenge of the storm surge induced inundation over the US East Coast. And then I will introduce a little bit the model, the high resolution model we developed here in Song Yixian University. And then I will show you some forecasting products over the South China Sea. And finally, as Professor Li asked me to show a little bit about the tsunami simulation for the March 11 tsunami, big tsunami. Since this is Professor Chen's work, I will show some slides over here. Okay, for the storm-induced hazard and desert disasters along the US eastern coast, not only for the hurricanes, tropical storms, but also got the extra tropical storms. This will lead to the coastal inundation, infrastructure damages, and human safety. This actually happened all around the world. And for the east coast of the United States, the response is different. And somewhere it has big waves, and somewhere is inundated very severe, and somewhere is not too much damage at all. This is due to the nonlinear interaction between the storms. And these are some pictures shows the coastal erosion and inundation, all of these damages. And even you build a seawall, but still the waves is going to splash over and you will have the inundation. So right now, the Noaa, the official Noaa storm forecast model system is called SLOSH. It is a structured grid surge model very efficiently, but there is no tides, no waves, and so lost of a lot of physics in it. So actually, the real observed elevation is not equal to the tidal elevation plus the storm surge due to the nonlinear interaction. And the wave current interactions can introduce radiation stress, change the current amplitude and directions, larger sea level, all of this. And at the same time, the waves splashing overtopping can cause the damage. And since the irregular geometry of the coastlines, basically the unstructured grid model needed to be used in such a kind of simulation. Well, Professor Chen, he simulated several scenarios in the past, now, and in the future, and how this coastal city along east coast of the United States to response. And he also compared 3 different unstructured storm surge models, ADSEC, FECOM, and SELF. And basically these 3 models performance is pretty same, but there are some difference. So the question right here is, what level of the change would we find for the storm-induced coastal inundation? And how it's going to develop an end-to-end forecast system for the storm-induced inundation with counting of sea level rise? What is the next generation of the storm surge forecast system? And basically, in the coast, we basically count for tidal elevation plus the storm surge and the wave run up. This is Zhuhai, my city, and it's always been flooded when the typhoon landfall. So since for the ocean is a multi-scale physical process, you have the conveyor belt over 10,000 kilometers, basin scaled 1,000 meters, and coastal away to the high frequency waves. So how to build a model to include all of these different processes? And in Tsunami University, we developed a ocean forecast model we call CSUM, and it includes 3 levels nested from global to local to the near coast. And this model has been deployed on Tianhe second, the supercomputer, and it's run cozy operational runs 24/7. And every day it costs a lot of money, about $300 US dollars. That's pretty expensive. Well, this is our model mesh, and we can see we have the very fine mesh near the coast, and at the South China, in the South China Sea, the Xisha Islands and Nansha Islands, we have around 200 to 300 meters resolution, and this will consume a lot of computer resource. And we have a local regional weather model, which is WRF, and the area is covers the whole eastern coastal and South China Sea, and the model resolution is about 3 kilometers. And this is our surface current we simulated in the South China Sea. You can see it includes the tides, and the tides is reversing, and we can move a little bit. And so with the high resolution model, we can, unlike the structured models, we can, we just have more meshes in the region where we do care. And in the open seas, we can just have the relatively cross resolutions. And this is Dongsha area, and these small islands we can resolve, and all the different small eddies, and we can see in transient eddies, and this is the Xisha Islands, and we can see all of these changes for that. And this is, we can zoom into the Bay Area. Actually, is this region is the most developed region in China, and right now we all care about the the inundation process over the Bay Area. And if we are going to simulate the inundation, and we have the mesh grid on the land also, that's since our model has the wetting and dry process, so we can deal with the inundation. And this is the Pearl River, Zhuhai, my city, and this is Shenzhen and Hong Kong. And recently we update our inundation models grid, and we include the big bridges, piers, more than 300 piers in the cross the mouth of the estuary, and near this the resolution is very high, it's almost 2 meters. And we find some observation data and compared with the water level and the currents, and the model performance is pretty good. And we also simulate with the sea level rise background and how it's going to inundate it in the Greater Bay Area. And we can see to 2050, the most coastal region of the Guangdong, Hong Kong, Macau, Great Bay Area are in the risk of the flooding. And the region is pretty much same as these guys, they use the satellite images to project. And this is major tracks of the typhoon attacks the north coast of the South China Sea. You can see the twin peaks, surge peaks, and the coast trapped waves. All of this is going to severely affect the Great Bay Area. So this is 2017, the biggest, one of the biggest typhoon Hedo hit my city, Zhuhai, and we can see this is the typhoon track, and the most storm surge high level water happened at the upper end of the Pearl River. And we find some observations, water level, and we compare with our model, and it seems our model performance is pretty good. And this is another one in 2018. Actually, these two landfall, these two typhoons landfall, it's almost the same place, but this time the highest surge place changed into the west coast of the Great Bay Area. Area, but also along the west coast and the east coast, and we compared our model and the observations, and in both of these typhoons we can catch the surge process. Oops. Okay, this is the whole coastal area inundation and the inundation movie to show how it happens. And this is a Great Bay Area, and this is the Hong Kong, Macau, and Zhuhai Big Bridge. Let me jump a little bit. Yeah, we can, since our model resolution is very high, we can solve the, this in transient eddies when the flooding and ebbing and behind upstream or downstream in the bridge piers. And oops. Okay, this is actually, this is my office right here. I'm sitting here, this red building, and this is a Zhuhai campus of Tsunami University. And we calculate we hindcast the typhoon Hato's flooding process. And actually, yeah, we have pretty high resolution of the land height along the coast, but for the since our model resolution around here is 2 meters, and so but the water depth, we don't have the exact our water depth is not so accurate. So so the flooding process is not so accurate, but we can see the our model can catch the can have the all of this kind of model result. And okay, now I shift gear a little bit to talk about the tsunami Japanese Daiichi reactors hit by the tsunami, big tsunami. And before we can see these reactors 1, 2, 3, 4 is over here, but after the tsunami wave hit, and you can see the front buildings are still here. It's okay, but the buildings behind these are damaged, totally damaged. So this is a tsunami wave simulated by Professor Chen at UMass, and he got a very high resolution of the water depth, and so and the seismology waves was generated by Lingjian from Wuzhou, and we can see the tsunami wave propagating and hits the east and west coast first, then get into the bay. And this is here is right here is just the Daiichi nuclear plant site, and we can see how the tsunami waves are propagating, and that makes very severe damage. And the tsunami wave is more than 10 meters, the highest. Okay, this is the movie shows how the Japanese, they built 2 jetties to prevent the wave heat, and they built this, and the nuclear reaction site is over here. But when the tsunami waves hit, the currents come over and waves hit, and these 2 jetties lead to a wave guide, and so that's why the the buildings behind this has been damaged, since these 2 jetties lead to the guide. This is totally depends on how the waves comes from, and you can see the second wave is also comes and can make the big damage of the nuclear disaster. And this is they calculate these ground dots are the background of these regions, the nuclear stuff. I don't know how to say the seasons, 137, and this line, the peak is actually 1986 Chernobyl, previous Soviet Unions. That's accident, and but still, compared to the Japan's this Daiichi damage, this concentration is really high. So in the future, all of this Japanese government is going to release this wastewater and into the region, and is going to have a big environmental impact. And this is Professor Chen. He simulates how the nuclear waste is like a dye, how it's going to be spread and dilute in the regional seas. And it seems the water here is pretty sluggish, and after 1 month, it's still hugged in the coast of the Japanese coast. So this is just a basic information to see how this wastewater is going to dilute it and dissolve into the ocean. Well, that's pretty much, I think my time's up, and that's pretty much what I'm going to talk today due to the limited time, and I will leave the summary here. And finally, I would like to thank everybody, and just like the previous talker, Dr. Yang, and I would like to make some friends here, and we can collaborate in the future to do some more good work on the coastal inundation. Thank you very much.
Thank you very much, Dr. Diana Su. It's amazing that you have a storm-surge forecasting system for all the south part of China. It's
Yes.
small, precise. Along the coastal is about 10 meters, right?
Well, actually, our model grid, actually right now we have the Great Bay Area. We have refined our mesh model grid, and the finest resolution is about 2 meters.
Wow.
Yes, very high. Very cost money. It cost me $300 per day.
Okay, to simulate that much high resolution models for all the southern part of China, say for typhoon, say 5 or 7 days, how much time, computer time?
Oh yeah, actually our typhoons simulation is using, right now we are testing the coupled our ocean model and coupled with the we're still testing with the atmospheric model. And for the 3 kilometers, since our computational domain is very large, covers the whole China. And so it's very time consuming. And I use about 6 cores of the Tianhe, the supercomputer. It takes 3 hours to simulate for 3 days. But for this one, but for the inundation model, since inundation, we don't need too much vertical levels. Even our model resolution is very high, 2 meters, the smallest one, 2 meters. But since we don't have too much, it's almost, because if you study the inundation, you don't have to have the clinic, just like salinity and temperature or density, all of this, we just use a barotropic, and the calculation is pretty fast. Actually, it takes 3 hours for 5 days prediction.
Okay,
If
thank you.
I use
Dr. Fu. Now it's my turn. So
okay, sure. Okay, I will stop. Okay, go ahead. It's your turn. Thank you.
Hello.
hello.
Hello, I am Kalayani Pornpinetpong. I am going to present for Miss Galmadi in Soy.
Okay, I need to upload my PPT file.
Let me share my slide.
Well, okay, now I got it.
You got the slide?
Yes,
Do you see the slide?
yes, I see, but do you see my slide? I want to upload my PPT file for my presentation.
No. No.
Oh, everybody, can you see my PPT file?
Yes, I can see at least, but it's in half. I only see half of the presentation.
Do you see the slide? It's full screen or half?
It's not mine.
Did you see now?
But it's not mine. I want to.
Okay, somebody has to stop sharing the screen first, then you can share yours.
Yes. Okay. The one who shared the screen, would you please download, turn off, so that I can share mine. Please turn off your screen. I want to upload mine.
Dr. Lee, probably you can share your screen now.
Yes, okay. I do that, but do you see my screen, my file?
No, sir, we cannot see your presentation.
What happens if I push share screen?
You have to select your files and
Yes, I did. Now you can see.
yes,
Okay.
yes.
Okay, I will talk about the problems of conventional modeling system we are using for monitoring and forecasting of inundation and erosions. And we'll discuss about how to overcome the limitations. My name is Dongyoung Lee. I'm working for Ocean University, China. So I will discuss about first some sample case.
Excuse me, sir. Can you display it in a presentation mode, please?
Can you see? No?
Not the full screen. You have to hit the
I need to hit what?
You have to
play
click the
buttons.
presentation mode, please.
Full screen. You need enlarge your presentation full screen.
Yeah, you may hit the
Professor Lee, there is a play button on the top panel. If you move a little bit to the left, there is a play button you can see. It's in Chinese. I'm not sure you can read it, but if you hit the play button, you'll be able
the
to.
first one is paste.
Yeah, but it's blocked by some.
Go left. Go left. It's okay. Up, up.
Is this or no? I cannot push it
The
because
bottom.
You move down a little bit, you will see the first one is paste. 粘贴, the second one, and the third one is from.
But, a little bit strange in my computer is the bottoms, bar is blocked. I cannot find. It means that you cannot see the full screen of my slide.
Yeah. Yes.
How about
The right bottom, you can push F5, push F5 button, F5 button.
No.
Bottom is blocked, so I cannot. Okay. Well, I have a problem. I cannot push in the. Which this one? This one. So this blocked. Okay.
那儿有个从当前开始，你看到，哎 ，hit 那个当前开始。
Now.
No, not this one.
Now it's okay.
Okay.
Okay, it took some time, so I'll shorten my presentation. Okay. I will talk about first we have to tell which cases the conventional models can handle, and we have to tell which cases still be a problem in forecasting and predicting. So we have to identify the first the problem that you can solve, you can predict using the conventional model, like tide, storm surge, wave, coupled models. I think we have to build, integrate all information, build a system, and establish the operational forecasting system, just like Dr. Su presented. That kind of storm surge predictions is feasible using the conventional models. But there's a lot of problems that you cannot solve using conventional models. For example, inundation and erosions occurs mostly at the swash zone. Just the total water level rise, we cannot predict. Say, total water level rise and added about swash motions by wave or swell or integrated wave. That kind of wave motion, swash motions, combined with the total water level, it will cause lots of disaster. So for that case, we need to identify what's the problem, why you cannot forecast, why cannot predict, why the inundation and storm surge. And if we identify the problem, we have to find out the solutions. And maybe probably through international cooperations. And then we can build effective coastal predictions and management systems. Say, let me give you first some example. So this is inundations at the 5 Pacific islands north of New Guinea, Papua. Say the storm was a little far from the area in the northern part of the Pacific Oceans, and the wave, the pressures set up at this area is pretty low, and wind is not so strong, wave is also not strong. And at that time, tide level is pretty low, but they have very severe inundations for a few days in the 5 Pacific islands. These kind of inundations cannot be predicted using conventional wave average models like FECOM, Deltares, or Telemac. We cannot solve this problem. This is derived by swell or infiltrated wave swash motions. So we have to apply wave resolving models. And the problem is how to provide the boundary conditions. So this is an example of inundations. Say, it's different from the inundation by storm surge. So it's time dependent. The low waves coming and approaching and going back. So the kind of swash motions. So how we can solve this problem is our concern. Say another example is we have a very serious inundation in the southwest coast of Korea while the typhoon is passing through. Typhoon name is Winnie in 1997. Along the China coast, near the typhoon landing place, of course, we have very severe storm surge. This kind of process can be predicted using conventional model, the storm surge model, because it is derived by tide, storm surge, and wave setup. The model tide and storm surge and wave coupled models can handle this. But the storm surge in the southwest coast of Korea is the pressure setup is maybe very small because it's far from the typhoon center, and wind setup is negative, is the offshore wind. And the problem mostly developed by the spring tide and long wave, the swell and infrared wave coming from here. So we have very severe inundations for pretty while. It was a big issue between two agencies in handling with the weather forecast and also hydrographic office. And they argue a lot, and it is a big event. And maybe classify the functions of the two agencies. So this is another example of, meteor tsunami. I'll not discuss this much, but this is very local. The tidal stations, 50 meters away from here, do not have this signal. Luckily, we have some signal from the videos at the seafood restaurant, and also I got some signal from meteorological centers, radar data. So if you assume that this echo in the radar is somewhat related to the pressure jump, I can simulate using the conventional storm surge model, as you see here, using the point source. At that time, there's another source, a line source from the northern part of China is propagated. We are thinking that these two long waves generated by one by point source, one by line source, meet at these areas. So about dozens of people was killed. It was a really big issue in Korea because radio and TV did this event very often because general publics care a lot because it can be their problem, their family maybe possibly enjoy holidays and then they can be died. But this kind of disaster is, the problem is providing the input data, but not much problem with the conventional models. This is another problem for tsunami that Dr. Su mentioned already. So I will talk that the total water level induced by tide, storm surge, and wave setup, that can be predicted pretty well using the conventional wave, storm surge, tide, wave coupling models. But the big problem is the inundations and the swash motions in addition to the total water levels. So we don't fully understand the processes. So in that case, the conventional method we are doing is using all the available parameters maybe produced by conventional models, and also, and then if we have a lot of data of result and all forcing term, we find some relations, some empirical statistical relations. So, but to do that, we need a lot of observation data, so it's not available. But for example, in Eurotop, in Europe, they do a lot of experiments in the laboratory and produce data, and then they build some formulas, the relation with the forcing term and environments and result. But it cannot represent all the nature environments. So anyway, for the problem, if the process is so complicated and the parameters, they interact each other, so there's nonlinear interactions, it's difficult to produce a formula. Probably you can use AI method using the machine learning approach. But to do that, we need lots of data, but such kind of data is not available. So this kind of, conventional method of empirical method is a problem because data is not so much available. The other approach is using the deterministic, if you understand the process well, learn the models. So some models is developed like XSpeech and Swash, or maybe Bushnet models. But this is also the problem is for wave resulting models, we need to provide proper boundary conditions, wave resulting boundary conditions, which is mostly not available. We just provide wave spectrum and generate a random number and generate some grouping, whatever, but we cannot simulate real situations because of lack of data. So anyway, the swash motions, which controls its impact, most of the swash inundations and coastal erosion is a problem because we don't have enough data to both approach, statistical empirical approach or using deterministic approach. So these two problems is very serious and is a main concern of the coastal engineering research these days to solve inundations and wave-induced erosions. Another problem is how to deal with impact of global climate change. For engineering applications, we need long-term predictions because to protect the properties, we cannot move, we cannot run away. We have to do some countermeasure in advance. Engineers have to design. To do that, we need the long-term predictions, like as the flood map, Dr. Yan and Deltares mentioned about that, and also to design the coastal structures, we need the design criteria. But we used to do that without considering impact of global climate change. When I do design wave determinations in all coastal Korea in 2005, and design storm surge determinations for all coastal Korea in 2010, I assume that there is no impact of global climate change. So it was very difficult to persuade people why I neglect the impact of global climate change, because many people complain that we have to use, but at that time, we have no choice. We cannot use that. With a strong support from Dr. Dean of Florida and also Dr. Goda in Japan, strongly support me. We cannot consider impact of global climate change in design because the area is so big, so you cannot use it for very expensive structures. But now it's 10 years past, and with the advance of science technologies, and I'm afraid that people will demand to include that. But the problem is we don't have clear answer to that. I think we have to work together on these three problems that we cannot handle that. So since we don't understand basic processes in swash zone is our area of interest because most of disaster, inundation disaster, erosion disaster occur at swash zone. We don't understand the process very well. So we need to develop new observation technologies to study detailed processes. Main reason we don't understand the processes is difficulties of observation technology. It's so dynamic, so shallow. So, for example, especially the sheet flow is very thin layers near the boundary, and we need a very precise micro instrument to measure the velocity and potential profile ground sheet flow. So development of instrument is a big issue. And then we need to carry out experiment in the laboratory and field. And if you understand the process much better, I think we can do much better in predicting inundations and erosions in the futures. So another problem is bathymetry is very sensitive. The process is very shallow. So the process is very sensitive to bathymetry, erosions and inundations. But bathymetry near the shore, especially the very dynamic, the sand beach, varies very fast. So our conventional method of surveying bathymetries cannot cover that. It's so expensive. You cannot so frequent detailed measurements to spot the inundations and erosions prediction near the shoreline. So we need to develop some cost-effective methods to monitor the detailed bathymetries, very fast changing bathymetry near the shoreline. We also need long-term accumulations of bathymetry data to develop beach erosions in the models and validate calibrate. So that is, I think, one of the big issues. Today, Dr. Yu from KIOS, he discussed about using the expanded radar. So it can be a solution. We can use video cameras because but the problem is if we deploy now, we can get data from now in the futures, but we need a lot of historic data to develop model calibrate. So for that one, we have to use available satellite informations. The Europe space agencies released open the Sentinel-1 and Sentinel-2 data is very high resolution, it's 10 meter grid size, and recurrence time is much shorter, it's 5 days. It's much shorter compared with the former Landsat, which is about 2 weeks. By using those remote sensing, we can find some solutions. But by estimating the shoreline, I think we need very detailed, accurate estimate of total water level to get the control. But it is also very urgent problem. And using the Sentinel data, the many bands, say for a few seconds, the time delay between the bands about less than 0.3 seconds. Using those data to monitor the surface information to derive bathymetries using the wave theories. I think the area is so big, so we need improved methods, more accurate estimations of bathymetries, both underwater and in the tidal zone. It's a very urgent and most important task that we have faced. I believe that coastal radar and video will solve the problem. So another problem that I already discussed that the two methods we can handle bathymetry, inundations and erosion at the SWAT zone, say statistical or empirical method, and using the wave resulting models, we have a big problem in applying because we don't have enough data to implement. So even though we have a very nice tool, if the data is not available, so we cannot use that. So main problem we have is we need data to develop models and have a detailed bathymetries and provide essentials input data to operate the models. That is the most important problem we have faced. we have to solve this problem through by establishing the cost-effective monitoring system, and then the forecasting system can be solved. As I mentioned, long-term prediction is essential for engineering, adaptations for coastal disaster, like preparing the flood map, design criteria of coastal structures, and shoreline and the morphologies changes. So to do that, if we predict, a lot of, not so far away, probably we can use conventional method using hindcasting. But if you do forecast, say maybe 50 years, 100 years, the existing method is not working. We have to consider the impact of global climate change. So right now, the global climate simulation model and also the global and regional and local model with the global climate simulations is not accurate enough. There's a lot of errors. So how to reduce the errors? So we have to use working with the global models. Dr. Yan and Dr. Su, maybe those models can handle the global, but we need measurement data to solve this problem. So it's so we need also long-term accumulation data to solve. So these three essential problems to solve the problem I'm talking, the main problem is the lack of data, how to collect the data that we don't have to solve the problem. So I think we are gathered here today. One of the most important issue is to initiate the cooperation program, and how to initiate this cooperation program. Still, we need a lot of processes to be selected. I think the most important selection process is we have to prepare very good proposals. I think if you have very good proposals, it can be used, it's very helpful to initiate this program, innovation program. And also it can be used by the participants to initiate the national or provincial or local program of innovations and erosions. Because these two is the most very important issues of most countries. If you prepare very nice proposals, I think there's a good chance to be adopted. So how to prepare? So I mentioned here, first we need to identify what's the problem. Why we cannot predict well inundations and erosions. And that's the derivations of research topic we choose. And find out the way to overcome the limitations. So that's the method on research proposals. So I have lots of slides to discuss our detailed specific issues, but I'll skip most of them because we are a little far behind the schedule. So how to write wonderful proposals is the most important. So we need to identify what kind of problem we have to solve, why we cannot handle important issues of inundations and erosion problems. So we have to identify how we can solve it. It can be a method. So and another issue is we need to promote the cooperation research, so we can prepare, papers, and then maybe publish and many, people of national and local can understand the problem. And also we need to prepare brochure to tell the general public and the government officers can understand the problem well. So how to prepare good proposals and how to promote the research, cooperative research, these two is the most important task. So I discussed about the problem we have. It is research topics, and the way how to overcome the limitation is the method. So I have a last most slide, but I'll skip. Let me talk just a few. For example, the monitoring program, we are talking about wave-induced disaster, inundation, and erosions, in addition to the tide and storm surge induced. So recent, the last 20 years, the advancement of wave models very much, and we can predict wave very accurate these days. You can see very small slide picture here. So anyway, we can produce forecast pretty well. Maybe 1 day, 2 day forecast, very good. Compare, so one of the main objective of wave monitoring system before is doing the service to provide wave information to the users. Wave monitoring points provide information just at the site of buoy and just information in the past. But wave models can produce information in the past at every grid point and also information in the future. The user will be much happy with the service provided by well-calibrated, validated wave models. So we need to focus wave observations. The observation should be very accurate to be able to calibrate, validate wave models. I'm afraid that many cases, observation data is not so good. In cases much worse than models data. In that case, it's of no use. So we need to calibrate, validate, and very accurate measurements is most important. Otherwise, I think it's almost useless. And another issue is models cannot provide many information that we need, scientists, engineers, we need to do detailed research. For example, the time series of surface elevation, wave height, extreme biggest wave, a series of big waves, so we call wave grouping or infrawave. Or these kind of information are very essential to develop coastal inundations and erosions prediction system. But this data is not available from the wave models. Wave models just produce some statistical information, not detailed wave information. So, but many cases, the buoy data, the time series, they just store it. They don't analyze or detail, just use wave spectrum or significant wave height. So it's a pity that we don't make most of the data, and we need to develop better system that can develop, produce essential information that wave models cannot produce. So I'll skip, we can use many methods. Say, for example, the details understanding the processes of a sludge storm, including sheet flow. We need a very precise instrument. In Ocean River, China, we try to do experiments, using some side-looking video. Side-looking videos can monitor the profile of bathymetries, maybe every second. So from which you can get sediment flux, you can calculate. But we still need concentration profile. But using the effective intensity and get a relation with the sediment concentrations. So we have a problem to doing that at the nearby sheet flow. Concentration is too high and the signal is saturated. Even the concentration difference, the signal remains same. So we need to solve those problems. And also we need to, monitor the sheet flow, velocity and concentration profile. This is a system that KIOS build and provide us. So we have some problem with the sensor, we have to improve that. Anyway, developments of instrument to be able to carry out research in slide shown is important, together with the monitoring of the beach profile. As I mentioned that, even we have nice models, if you cannot provide boundary conditions, ocean boundary conditions, we cannot use it. At present, monitoring system cannot provide essential information to predict wave-induced inundations and erosions. So we have to improve the wave monitoring system is essential. I discussed about the monitoring of bathymetries. It's very important, and we can use cellular remote sensing, and also we can use video, and we can use radar. So I carried out 4 experiments when I was working in Korea, 2 experiments in the east coast of Korea, and 2 in the west coast, different environment. At that time, the purpose is to validate the function of the radar. I was thinking to combine with the subsurface pressure sensor and the radar combined, and to build the national monitoring system to get the full 2D wave spectrum and also long wave. But some result experiments not satisfactory to meet my requirements. So we stopped using that for national wave monitoring. But since I came to China, I keep working on coastal erosion problem. So it can be used very well for monitoring bathymetries together with direction wave spectrum, as Dr. Yu has discussed today. So I pay much attention on this. So probably we can develop much better methods to derive bathymetries and 2D wave spectrum from radar and also video, so that the problem of providing the accurate input for wave resulting model and also for empirical models can be solved. So another issue is the wave, infragravity wave information. We don't have detailed mechanisms, generations of infragravity wave in the oceans. Generations of infragravity wave near the shore by wave interactions is pretty well. We can do some prediction, but over the oceans, to do that, we need to have global models covering all the oceans of Pacific, and also we need data. But to build the data just to measure this infragravity wave, I think it's infeasible. It's so expensive. So they already established the DART system to monitor the tsunami. I think we can expand it with very little expenses to include monitoring of swell and infragravity wave. And then with the global models covering all Pacific oceans, we can get better knowledge, understanding to be able to predict ocean-induced swell and infrared wave, which is very, very important for the inundations and erosions forecasting. So anyway, I'll not discuss much because I spent so much time in it. So I can say that it's time to build, integrate coastal observation and prediction system now to cope with the coastal hazard. We tried that, maybe 10 or 20 years ago. At that time, there's a lot of problems. The technology is not so much available, model is not available, data is not much available. But these days, many process-based models is available. Deltares have released many models, Delta modeling system, and also any other good models available. And the forcing information available, and intensive observation data is available, and you can develop monitoring system technologies, and computation is much faster now, and the data memory is improved a lot, so you can build nice database and modeling system. So the problem is how to improve the monitoring system to meet the requirements for the accurate predictions of coastal hazard system. This is what we need to solve jointly. Well, I'd rather stop here. So maybe if there's no questions, we'll move to next presentations. Any questions?
Hey, Professor Lee, thanks very much for your presentation. Maybe rather a question, perhaps a comment rather than a question. Yeah, as you mentioned in your presentation, there was in general, there was a lack of data, boundary conditions, climate information that helps you to do the early warning, the reconstruction of the historical event, or looking at the future scenarios. I think that's exactly why we're here. Our goal is actually to build such a global systems, global models, data set that helps to provide such a boundary conditions. And for the waves also, there were already actually quite a lot of global data sets and models which are freely available out there that helps you to provide the boundary conditions to provide to connect to your models. For example, in forecasting, wave watch, and also from ECMWF Aero 5 reanalysis, those are also a good data sources. So yeah, I'm happy to see this, and as I said also in my presentation, we are happy to be on board and to help as well.
Okay, thank you very much for your comments. So we cannot build the data system, modeling system. It would be very expensive to build all the information we need. So we have to identify what we can do, what can be achieved in over decades, and we can have priority. So what we need to achieve to do good predictions of coastal hazards. So we need to discuss, we need to have more specific plan and co-design the proposals. And I hope that we can work together to solve the problem nicely. Okay, thank you for your comments. So if there's no other comments or questions, we'll move to next presentations. So next presentation is by Taiwanese. The three ladies is working together, and Mrs. Kalayani will present on the next sessions. The topic is how to preserve and rehabilitation of natural resources. So because of inundation and erosions, we have problem with the loss of natural resources. How to preserve it is the topics. Maybe she will explain the examples, what they are doing in Thailand. Dr. Kalayani.
Hello. Hello.
Okay, yes, go ahead.
Good afternoon, Dr. Lee, Professor Lee, and everyone. Thank you very, very much for inviting me to join this meeting. Let me open my slide.
So I need to know my slide.
Can you see the slide? Did you see the slide?
We can see the slides.
All right.
So it's still mine. I think I have to.
I saw your, yeah.
So how can I?
And revitalization of nature and cultural resources. This is your slides.
Yes, how can I down my slide?
You don't need turn off your slides. It's already changed to slides.
Now it's mine?
Yes, it's yours.
All right.
Okay, go ahead.
All right. Today I'm going to present for Miss Galma Insoi. So the topic that we present today mostly more about the storytelling, what's going on in Thailand, and most of problem from man-made problem, and we try to solve the problem for the beginning. For the coastline of Thailand, most of the coastline, 52% is a coastal, is a sandy beach. So we interested in the sandy beach because it's a high value of tourism. In Thailand, the economic value of tourism from the coastline and the ocean is more than half of the total of the tourism of the country. And how does natural beach system provide goods and service to people? In economics, we have identified the value of the natural resource as the 3 items. First one is the direct use value. The direct use value is mean the value from the natural resource that directly people use it. For example, about the recreation for the beach, and also the community can use the beach as their activity, daily life. Students also can use as a playground. And the one thing that's really important thing is the natural sandy beach act as the natural buffer zone. Look at it closely, you can see that the sandy beach is the most material for they can protect between the water and the land is hard. So this area, the coastline is the dynamic. So the sand can adapt themselves for when monsoon season or dry season. So people can protect the buffer for the land. And another item is the indirect use value. Indirect use value is mean.
Excuse me, ma'am. Your slides are not changing at all. Can you shake it up a little bit, please?
Oh, my slide did not change.
Yes, it's frozen at the first slide. Okay, now it's changing, and can you please show it, display it in the full screen, please?
Oh, all right.
Thank you very much.
All right, cool. So I'm going to talk a bit about the economic value from the sandy beach. The first one is direct use value that I already talking about. I would like to focus on the sandy beach as a natural buffer mechanism. Because on the coastline, the sandy beach can stay between the land and the water. And this area is the dynamic. So the good mechanism, the sandy beach is the good mechanism to stay there, to protect the land, and also people can use their factor. And the second one is the indirect use. For example, about the indirect use value is something that the natural they act as for themselves, but they produce something people can use it. Like a coastal area, they produce the fish product, and people can collect fish for their economics or their daily life. Also, all many kind of things, all many kind of animal along the coastline also can use some productivity from the beach. So this is, we call this is the indirect use value. But most of people we familiar with the fishery value. For the sandy beach system, the coastline, they can, this photo is show the sandy system from the coastline. During the monsoon season, the wave will bring the sand to the front of the shoreline. So it's become sandbar in front of the shoreline. It can protect the strong wave from the sea. And when dry season, the wave is low, so they bring the sand back to the beach. And also the wind can bring the sand on the beach go to the land. So it becomes the dune. The front dune is we call MDO sand dune, and also fall dune and yellow dune, and also mature dune. So this kind of system can create they can protect the water table. So the beach, the sand can protect the salt water not intrude to the land. That's why the plant and animal can stay on the land, can use the water, fresh water. And this area become the forest, coastal forest, and community will moving in to stay there. This kind of thing is in economics. We call this kind of thing people use from this system for a long time. When we lose it, it's going to very high cost for people for their daily life. The another value is very high value is a passive use value. It means the value that people feel good with the natural resource is something like existence value or bequest value. For example, about people can feel very happy when they know that the sandy beach is still there, healthy, even though they don't stay there anymore. They feel good because they know that this kind of natural resource can stay for their next generation. This one we call passive use value. In Thailand, now we face with something that's coastal erosion. More than 30% is got erosion, and we can say that all of them because from man-made construction. So this is issue. We try to reduce the reduce the erosion caused by man-made because it's if we can control it, it can help a lot for the natural. Our group is interested to select some part of the coastal area for the sample of the try to protect this area and try to restoration for try to bring the natural back. The good example is the sandy beach in front of Malukatayawan Palace. This is located in Phetchaburi province. This photo from the past. The Malukatayawan Palace is here. Was built from King Lamarsik. And in the past, this area is very healthy area. You can see that the sand passed by in front of the palace. There are two areas. One is from the south and another from the north. This is bring the sand from the land to the sea, and some sand also from the south of Thailand.
ขออนุญาตค่ะคุณกัลยาณีคะ
ค่ะ
ถ้าคุณกัลยาณีไปตรงการนำเสนอภาพนิ่งได้ไหมคะตรงแถบบาร์ข้างบนนะคะ
แถบบาร์ข้างบน
การนำเสนอภาพนิ่งค่ะตรงข้างๆคำว่าภาพเคลื่อนไหวนะคะตรงข้างล่างแถบสีแดงการนำเสนอภาพนิ่งเห็นไหมคะ
ไม่เห็น อยู่ตรงไหนนะ
อยู่ตรงข้างล่างแถบสีแดงอะค่ะข้างล่างแถบสีแดงด้านบนของจอเลยค่ะบนสุดของจอเลยค่ะจะมีแถบสีแดงใช่ไหมคะแล้วจะมีคำว่าการนำเสนอภาพนิ่งอยู่
ของสไลด์ใช่ไหม
ค่ะใช่ค่ะ
ของ PowerPoint ใช่ไหม
ใช่ค่ะ
ค่ะโอเคเห็นแล้วค่ะ
มีคำว่าการนำเสนอภาพนิ่งเดี๋ยวคุณกัลยาณีกดแล้วก็กดออกจากภาพนิ่งปัจจุบันนะคะมันจะเป็นจอใหญ่ขึ้น
ค่ะนี่กด presentation ได้ไหมคะ
ได้ค่ะกดเป็น presentation ก็ได้ค่ะ
ถ้าแรกกด presentation แล้วมันไม่เคลื่อนไหวเดี๋ยวลง
มันไม่เคลื่อนใช่ไหมคะอันนี้เป็น100%หรือยังคะ
เมื่อกี้กด presentation แล้วมันไม่เคลื่อนไหวก็เลยเดี๋ยวนะนำเสนอภาพนิ่งใช่ไหมแล้วก็กดตรงไหนนะต่อไปนะคะ
จากภาพนิ่งปัจจุบันนะคะ
ภาพนิ่งปัจจุ
จาก
บัน
ด้านซ้ายมือค่ะจากภาพนิ่งปัจจุบัน
ค่ะ
มันขึ้นเป็นจอใหญ่ไหมคะ
ใช่ดีขึ้นไหมคะดีขึ้นแล้วไหม
ยังค่ะ
เหรอคะตอนนี้มันหน้าจอพี่มันขึ้นแล้วนะ
คุณกัลยาณีเปิดเต็มจอได้ไหมคะตอนนี้มันเห็นแบบแค่ครึ่งเดียวอะค่ะ
นะคะตอนนี้มันก็เต็มจอตอนนี้มันเต็มจอแล้วนะ
คือตอนนี้ของผู้เข้าร่วมเขาเห็นแบบจอมันไม่เต็มอะค่ะเดี๋ยวกดขยายจอได้ไหมคะกดตรงช่องสี่เหลี่ยมข้างบนนะคะมุมขวาสี่เหลี่ยมตรงข้างๆกากบาทนะคะ
ค่ะเดี๋ยวนะเดี๋ยวนะ
มันไม่ได้
ตรงสี่เหลี่ยมมันบังมองมันกดไม่ได้ตอนนี้มันครึ่งเดียวเหรอคะ
งั้นไม่เป็นไรก็ได้ค่ะงั้นเดี๋ยวทำแบบเดิมเลยค่ะแล้วคุณกัลยาณีเดี๋ยวรบกวนกดตรงสี่เหลี่ยมข้างๆกากบาทอีกทีได้ไหมคะ
เดี๋ยวนะคะ เดี๋ยวนะครับคือมันเป็นเพราะว่าคำสั่งอันนั้นเนี่ยมันบังตรงกลางกับบังตรงสี่เหลี่ยมทำให้พี่กดไม่ได้ค่ะไอ้ตรงคำสั่งของซูมอะค่ะทีนี้มันเอาออกได้ยังไงไม่ทราบออกได้ยังไงเนาะมันบังตรงสี่เหลี่ยมทำให้พี่กดไม่ได้
คือไม่รู้เขาเป็นเวอร์ชันคุณกระยานี้ค่ะตรงด้านล่างจอมันมีให้กดเป็นเมนูไหมคะที่ปรับสเกลของไซส์ตัวสไลด์มากสุดเลยพอดีของฝั่งจะเห็นเหมือนตกตอนนี้นะคะใจด้านล่างของจอ
เดี๋ยวนะสักครู่นะคะตอนนี้เลยเดี๋ยวนะตรงไหนนะคะ
ตั้งค่าตรงการนำเสนอภาพนิ่งเราเป็นตั้งค่าค่ะแล้วมันขึ้นเมนูด้านล่างค่ะเหมือนตอนนี้มันอยู่ในโหมดแก้ไขอะค่ะ
มันหาไม่เจอขอโทษด้วย
หรือว่าลองดูตรงมุมมองได้ไหมคะเมนูก่อนสุดท้ายอะค่ะที่เขียนว่ามุมมองตรงแถบสีขาวค่ะจะมีเขียนด้านบนนะคะ
ไม่เห็นมี
ตรงเหนือสไลด์อะค่ะจะมีเมนูเขียนว่าแฟ้มหน้าแรกแทรกแล้วก็ไล่ไปเรื่อยๆอะค่ะค่ะแล้วตรงที่เขียนว่ามุมมอง
ค่ะแล้วยังไงต่อไปนะคะพอมุมมองแล้ว
ว่าเหมือนจะเป็นคนละเวอร์ชันกัน
คนละใช่มันไม่เหมือนกันตอนเนี้ยตรงสี่เหลี่ยมเนี่ย
คือตรงปกติด้านล่างอะค่ะมันจะมีเมนูให้ปรับย่อขยายอะค่ะมีไหมคะ
ค่ะ
มีไหมคะด้านล่าง
ถ้าอย่างนั้นก็ใช้แบบนี้
ไม่ค่ะแล้วมันจะมีรูปที่เป็นจอใหญ่ๆแล้วเขียนว่าสไลด์โชว์อะค่ะพอดีผมไม่เป็นภาษาอังกฤษเลื่อนลงไปด้านล่างจอให้ได้ไหมคะด้านฝั่งขวาค่ะแล้วก็เลื่อนบาร์ลงไป
มุมมองการอ่านมีมุมมองการอ่านมี presentation
เลือก presentation ได้ไหมคะ
ค่ะเลือก presentation ใช่ไหมอันนี้ใช่ไหมมันไม่ขยับอะพอ present ไปแล้วภาพมันไม่ขยับใช่ไหมคะ
มันจะต้องขึ้นเป็นเต็มจอค่ะมันจะมีแถบให้เลื่อนที่เป็นบวกลบใช่ไหมคะมันจะเป็นรูปสุดท้ายก่อนตรงแถบเลื่อนบวกลบ
Excuse me. I think we are well behind the time schedules, so we have to go ahead. Would you please finish your presentation?
ถ้าอย่างนั้นไว้แบบนี้เลยก็ได้ค่ะ
เนาะเอาแบบนี้เลยแล้วกันเนาะ
ได้ค่ะ
ค่ะแบบนี้พอโอเคไหมคะ
ได้ค่ะขอบคุณค่ะ
Okay, please go ahead and finish as soon as possible.
All right, okay. Sorry.
Schedule.
Okay. So this photo is about the area of the Melikayawan Palace in the past. So we can see that this area is so much sand dune and agriculture area and also water channel. Water channel is two channel. It's over here is this photo show that you can see on the top of the photo the Melikayawan Palace. Some year the when the high wind and high wave, so the sand will move up a lot. But some year is more, some year is less. So sometimes they too much worry. When they worry about the erosion, so they put the rock in front of the palace, and then they cause erosion nearby. The top photo. When you put the rock there, the problem is the natural cannot bring the sand back to the front of the palace. We still got worried, and then the below is, you can see 2 jetty in front of the water channel. These 2 jetty is the purpose of the jetty. They can, some project try to do the artificial mangrove inside over here. So they need the salt water. That's why they made the jetty, try to bring salt water, get in the land, and try to do the artificial mangrove. In fact, this area is not artificial, it's not mangrove area. It is a forest, coastal forest area. The problem with, after put the 2 jetty over here, they cause erosion in front of the palace. It's very severe erosion. And then they put breakwater and another groy in front of the palace. So many kind of the construction put there, and the sand still lost. So we can see that the sand is cannot move it in because the construction will obstruct the sand. And another problem is over here is when the water, the seawater intrudes to the land. So we lose of the water table. The fresh water over here, people cannot do agriculture, and also the fresh water in the palace. It's cost very high to bring the fresh water outside to use in the palace. Another problem is over here, because this construction will cause erosion up to the north to the tourism high-end area. That area erosion will cause until the Cham, and also very far away. After erosion, they can also put another breakwater, try to protect try to solve the problem, and also will cause the end effect. Erosion still occur. So now, what the impact of this activity from the jetty and construction? First one, we lose the fresh water on the slack of the sand dune. The second one is the mud and sediment will fill in the salt marsh area. And also sea water intrude to the land. That alien species will occur, introduce over there. So we lose of the formal species, and also lose of the groundwater, also beach erosion. What we're going to do now, in front of the palace now, we try to remove of the some of the construction and try to do the sand bypass, try to bring the natural back to here. And also some problem is about the fresh water. Fresh water now still thinking that how to bring it back to natural. Lesson learned from the beach erosion over here. First one, because the miss of identification of the problem. First one, we worry about some kind of the season that we lose too much sand, but in fact, the natural will bring back from the next season. And also when we do something, we incomplete to define the natural cycle. like we try to do the artificial mangrove on the coastal forest. Now it's high very cost to try to protect the artificial mangrove because it's not their place to grow. And also when we try to solve the problem, we use the innovation that against the natural system. So now we try to get back to try to solve the problem using the natural system. So now it's just, we just get started to use this place for do the experiment. And now the government just give us the authority to try to do the experiment over here. Thank you very much. And sorry for inconvenience for my slide.
Thank you, Mrs. Calarani. Oh, so time is over too much, and I'm afraid that some of the speakers or audiences have another schedule. So let's finish as soon as possible. Now the last speaker, Professor Yang Ping Chen, he will talk about how our program will contribute to solve others' ocean challenges. Dr. Yang?
Hello, buddy.
Yes.
Yeah.
Go ahead.
Okay. Yeah. I will change this.
Yes, please finish as short as possible, because we are behind schedule.
So limited.
So much.
Yeah. Good afternoon, fellows. I'm Bingchen Liang from Ocean University of China. My topic today is about coastal inundation and erosion research tackle the United Nations decade challenges. And coastal communities are facing disastrous climate impacts in the current and coming decades. We are under the risk of more severe and frequent storms, heavier rainfall, and associated coastal flooding and erosion problems. To better understand and predict the coastal inundation and erosion processes are relevant to diverse aspects in coastal communities and other keys to tackle most of UN Ocean Decade challenges. Due to a limited time, in the coming slides, I'm going to briefly introduce the relevance of coastal inundation and erosion research to the first challenges mentioned above. The first challenge is to understand and beat marine pollution because of the affinity of pollutants to cohesive sediments. As a result of adsorption, cohesive sediment transport plays an important role in characterizing the transport and the fate of contaminants input to coastal waters. Therefore, erosion characteristics and the transport of fine cohesive sediments must be known for predicting the fate of pollutants in the coastal environment. The second challenge is to protect and restore the ocean ecosystem and the biodiversity. Coastal flooding and erosion have threatened the ecological system and the natural resources, including mangrove forests and coral reefs and seagrass, which is in turn provide a natural defense against the future storms. Their loss due to erosion may indicate an increase in vulnerability from these hazards. To promote and maintain diversity of natural habitats and their ecosystem, restoration may be needed. In this process, the information of the coastal hydrodynamic and morphodynamics are necessary. challenge, the third challenge is to sustainable feed the global population, where coastal agriculture and fisheries play an important part. They are strongly related to the coastal ecosystem and the biodiversity, which are controlled by coastal hydrodynamics and morphodynamics. And this is the challenge for is to develop a sustainable and equitable ocean economy. Coastal flooding and erosion from severe storms can affect several economic sectors, such as coastal infrastructures and port operations. These economic sectors are relevant to a country's overall economy. And here, what can we do? First, we need to learn from the direct measurements of seawater properties. In-field sensors such as ADCP, CTD have the ability to gather meaningful data such as wave current, water temperature, and salinity. In recent years, the development of remote sensing techniques such as radar, and satellite have greatly increased the amount of ocean data available. And recent advances in this area have also resulted in substantial gains in data quality and reliability. All of this help us to have a better understanding of the ocean and prevent us from future hazards. And from a global scale, we have the Earth system that consider the macro scale physics of the Earth, including both atmosphere, ocean, and land. However, analysis and predictions from the Earth system model typically have coarse resolutions and do not consider the macro or macro characteristics. Therefore, for the research of coastal inundation and erosions, it is necessary to include a downscale process to capture the regional features. For example, as shown in the red panels, a downscale from global forecast system model to a regional weather forecasting model, WRF, with 1 kilometer spatial resolution. The rain band structure and the evolution of Hurricane Harvey in 2017 was well captured. In terms of regional model, different models can be applied to address specific coastal problems. For example, the SWOSH model can be used for simulating unsteady, non-hydrostatic free surface, rotational flow, and transport phenomena in coastal waters as driven by waves, tides, forces, and wind forces. With the advances in ocean modeling techniques, coupled atmosphere wave ocean models start to gain more attention and to be widely used in ocean predictions. For example, the coast modeling system developed by USGS provided two-way coupling among atmosphere, ocean wave, and sediment transport. Here is an example showing what we can do with coupling modeling system regarding the coastal inundation and erosion. The left panel shows the simulation flooding map along the US East Coast during Hurricane Michael in 2016. And on the right is the modeling wave field with errors editing the wave directions. The modeled water level and the waves were well validated with initial observations. In addition, Hurricane Michael brought about notable morphological change, especially at the Massachusetts Inlet. We can see the hurricane induced the morphological change near the inlet was well captured from the perspective of sediment transport from this picture. Furthermore, coupled numerical models can be applied to simulate the dynamics of estuary circulations, which is important in tackling the issues of coastal pollution, as mentioned in Challenge 1. Here is an example showing the modeling surface salinity and the spreading of alleged pollutants in the area of southwest Florida. So, in the end, although there is not one set fits all solution to all challenges, there are a lot of things we could do regarding the coastal inundation and erosion research. In addition to set up a more cost-effective issue observation system, we could build a comprehensive coupled modeling system oriented to multiple coastal hazards. This system may include modeling results from different specific models and a web application for data visualization, and access to all output products from the modeling system. This is crucial, especially under the threat of climate change, and become achievable in the area of the big data. That's all. Thank you.
Thank you, Dr. Yang. I think demonstrate our program can contribute a lot to 10 ocean challenges the UN is trying to solve over the next decades. It's very important to initiate this program. Well, thank you very much, everybody, for your patience to stay in these sessions, even time was delayed quite a lot. So we'll skip the discussion session today because of time delay. I think we can have another discussion sessions, we can schedule. I think maybe some, I guess, among the audiences, may be interesting in joining the discussions, we welcome. So important issue is how to initiate this program, how to prepare good proposals, how to promote this to convince them, and we have to plan a specific implementation plan, the coverage of the area or the method. I think we need to discuss a lot. So let's do that some other time, including some whoever interested in discussing with this to initiate this as a UN program. Thank you very much again, and I hope that we have a chance to work together to solve the problems for the people, and let's meet at the discussion sessions, discuss meetings sometime. You can schedule, we can discuss in detail. Thank you very much again, and have a nice evening.
Thanks a lot, Professor Lee, for organizing this. Thank you. Bye-bye.
What time is it in Netherlands now? Is it still early in the morning?
It is 10 a.m. in the morning. Yes, you're right.
Oh, okay. So we consider the time lag in Europe and America, and we'll schedule discussion time. Maybe we can do that in the Zoom meeting some other time. So we have lots of topic to discuss.
Sure, yes, glad to help. Let me know.
Okay.
Thank you.
Bye-bye.
Bye.
Bye-bye, Professor Lee.
Yes.
Bye-bye.
Bye-bye. Thank you. Bye-bye.
Bye-bye.
I'm sorry again, this delays too much. Probably some of you missed your schedules this evening.
Bye bye, Professor Lee.
Hi,
Mm.
iPhone.
Yeah, long time no
Long
see.
time no see.
Yeah. Yeah, we will discuss later. Okay.
Okay,
Bye. Mm.
so we'll invite you.
Okay, thank you. Bye bye.